All right, linearization and differentials. So linearization, we're going to be talking about linear things, okay? Lines. Differentials, which is kind of like derivative, right? So it's something related to that. It's really something that's simple. It'll be a good break from those optimization problems. And look at that. You can impress your friends by doing square or cube root of 70 in your head. All right. But you got to get pretty good. And I'll help you get there. This is something you can read this to yourself. Okay. Hopefully you are actually reading this. And so what we're doing is kind of using that tangent line to estimate. So that's pretty close to cube root of 70 on our function. So we're just going to be estimating using the tangent line. All right, and so what we do, like example one, let's get a color here. All right, why not blue? All right, so we need a tangent line approximation. So in order to have a tangent line approximation, we need a tangent line. So we're talking about using a cube root function. And our center, it's centered at 64. All right, so that's what we're focusing on. Right at that point, we're focusing on that tangent line that's coming across right there. All right, and so to find the tangent line, we're going to do f prime. We need a slope and a point. Okay, so that would be 1/3 x to the negative 2/3. Okay, or I could write this cube root of x squared. All right, so f prime of 64, our slope at that point will be 1 over the cube root of 64, which is 4, squared. So 1 over 3 times 16, which would be 1 over 48. That's our slope. Now let's find the point. If we plug in 64, what's the cube root of 64? Hopefully you know that. It's just 4. So now we pull those together and get our equation. Y equals 4 plus 1 over 48 times x minus 64. That's our tangent line. Tangent line. Okay, there we go. In case you're wondering. So we're going to call that the L of x for the linearization of this function. So we can say that cube root, and it's really important to use this notation because we are just approximating. We're not saying it's an exact value. So the cube root of 70 is going to be approximated by the linearization of our function at 70. So we plug this in, we get 4 plus 70 minus 64, that'll be 6 over 48. So that's 4 plus 1/8, and you know 1/8 is 0.125. So that'll be about 4.125. All right, so this, and it says here, determine if it's an over or an under approximation. All right, since, I'll put a little star here to separate, since f of x is concave down, okay, it is an over approximation because the tangent line lies over the graph. All right, so I didn't do both parts of this. Now it says do it using a secant line approximation, so I'll do that using these two values. So we have 2 points, 64, 4, 125, 5. So let's find the slope, change in y over change in x. Slope will be 1 over 61. We could use this point, write our equation, 4 plus 1 over 61 times x minus 64. All right, I'm going to call that k of x. Why not? I called the other one L. Oh, that's good enough. So we're going to say cube root of 70 is about equal to k of 70, which would be 4 plus 6 over 61, and that is about equal to 4.098. Now this is an under approximation. Okay, since the secant line lies below the graph. the graph of f. All right, so if we look at this point and we talk about this point down here, if we draw that secant line, hopefully you can draw it much better than I did. It actually lies below the function. Okay, so let's move on here. So this is basically what we did. You find the equation of the tangent line, leave it in point slope form, it's easier. All right, solve for y and rename it L of x for linearization. Okay, linearization. Plug in whatever our center is, okay? And you need to write that you are approximating that value. We're not finding the exact value, okay? And then usually you'll be asked, is it an over approximation or an under? And you know by the concavity. All right, so estimate the fourth root of 17. Okay, so the first thing we need to do is find the equation of the tangent line. Well, let's talk about what function. This time we're going to use the fourth root function. And a really close fourth root would be 16. All right, so if I plug in 16, I get 2. There's a point. I'll take the derivative. Okay, rewrite it if you want. Plug in 16. All right, I'm going to change those exponents so I could do it in my head a little bit better. The fourth root of 16 is 2, cubed is 8, 4 times that. So the slope is 1 over 32. My equation is y equals 2 plus 1 over 32 times x minus 2. And I'm going to name that L of x for linearization of x. Now we'll use it to approximate the fourth root of 17. All right. So we have 2 plus 1 over 32. Oh, wait, that should be 16. I don't know why I wrote a 2 there. Thanks for correcting me, guys. All right, 1 over 32 there, because 17 minus 16 is just 1, which is equal to 2.03125. All right, now this is an over approximation. Since f of x is concave down for all x bigger than 0. Okay, if you know what the fourth root function looks like, then that should be easy. If you don't, graph it, memorize it, why not? All right, so we're going to do at least one more example today, maybe 2. Change up colors for some fun. Is it an over approximated, and then is it an over or under approximation? So it looks like this time we're talking about the x to the 5th function. We're going to be centered about 3. That's close, okay? So get our point and our slope. Okay, 3 to the 5th equals 243. I'm sure you all have that memorized. F prime of 3, that'll be 5 times 3 to the 4th. And then that's, what, 405? Okay, so now I can write my equation. Y equals 243 plus 405 times x minus 3. And we're going to call that the linearization of our function. All right, and so then 3.01 to the 5th can be approximated by the linearization at 3.01. So we get 243 plus 405 times 0.01. Okay, we just move the decimal in 2 places. So we get 247.05. Now, here's my justification. F double prime of x. That's 20x cubed. So F double prime is going to be greater than 0 for all x bigger than 0. So F is concave up, and L of x is an under approximation. APPRX. Okay, there we go. So we'll do one more and we'll save the differential stuff for the next video. All right, we'll finish this out here. Let's go with a fun color. This one. There we go. Nah, that's horrible. Looks like puke color. Maybe burnt orange, tangerine. All right, that looks fun, right? So what's our function here? Our function this time is ln of x. We're going to be centered at e to the 10. So f prime of e to the 10, ln of e to the 10, simply 10, right? F prime of x is 1 over x. F prime of e to the 10 will give us 1 over e to the 10. So even though this looks scary because it's an ln function, it hasn't been bad so far. All right, write our equation. X minus e to the 10. And we're going to call that L of x. Okay, so ln of e to the 10th plus 5 can be approximated by L of e to the 10th plus 5. Okay, that'll be 10 plus 1 over e to the 10 times 5. All right, so we can approximate it as 10 plus 5 over e to the 10. You could get a decimal if you want, but I like it just like that. Now, this is, since f is concave down. I know that because ln functions are concave down, like a frown. All right. The linearization of x is an over approximation because it would lie above the graph. All right, so I hope you have a concave up like a cup kind of day. See you in class.